So today we are going to be talking about disk based data structures. In the last class we looked at AB trees. So these were an extension of the 2,4 trees that we had seen. Today we are going to look at disk based data structures. In particular we are going to look at B trees, and we will see that they are very similar, or they are in fact AB trees for a specific value of B. Okay, and the setting now we are looking at is when we have a large amount of data over which to search. Okay. So, till now all our search trees were limited to main memory, in the sense that you build a binary search tree or build a 2,4 tree or a red black tree. So, we had these nodes which were objects in memory, and the references correspond to pointer addresses or addresses, memory addresses. Right. Now, we are looking at a setting where we have a huge amount of data, let us say some kind of transaction data, which could be banks, stock markets, settings where large amounts of data get generated. And such huge amount of data is not stored in the main memory of a computer, right. This is typically stored on disks. And now you want to be able to search through this data, or insert something into this data, or modify this data, right. How do you do that? So, just imagine a setting where you have, let us say, a particular bank which has records for each of its customers, right. So, there could be 1,000,000 customers, each of those records would be huge, right. The data associated with each account would be huge, because it would have all the transaction data associated with it, what has been the history of transactions and so on. Now, you can't expect all of that data to reside in the main memory of the computer. So, it would be kept on disk. And now, suppose I type in a particular account number, you should be able to retrieve that particular account and the data associated with that account. So, question is, how are you going to do this? Right. So, we want to make a search tree which is in some sense secondary storage enabled, which will help, even when the data or most of the data is stored on disk, we will still be able to search through it. Okay. Now, the problem here is that the data is stored on disk, that is fine, but even the index that we are building, right. So, what do I mean by index? The search tree. The search tree that we have is so huge that we cannot expect the entire search tree to fit into the main memory. We will come to this in a short while, right. So, what is the problem when you have things on the disk versus when things are in the main memory of the computer? So, one big problem is that disk access is very slow, right. So, how is disk accessed? You have, let us say, this is a disk. So, you typically have a bunch of disks, stacked one on top of each other. Each one of them has its own read write head, a head which will traverse, which can move along this disk and get to a particular track. So, these are the tracks on the disk, right. The disk rotates in one particular direction, and this read write head can decide that it wants to go on this track or this track or this track, or so on and on, right. So, this part is called, okay. So, yeah. So, when you have to read a particular location, so a track is further divided into sectors, right. So, when you have to read a particular sector, the disk rotates and this read write head gets to the appropriate track and then starts reading the data from there, right. So, a significant fraction of the time is spent in this read write head moving, determining which track it has to go to and moving, and the rotation, right. So, one of these is called the seek latency. So, the time that is required for the head to get to the appropriate track is called the seek latency, and the other one is called the rotation latency, the time required for the disk to rotate, so that the head is positioned at the right place, the right sector. And once you have arrived at the right place, then the entire sector is typically read. So, one sector, or let us say let us call it page. So, the data then is read in units, in larger units. You do not read 1 byte of data from the disk. Why do not you read 1 byte of data from the disk? Because you have already spent so much time in getting to that 1 byte that you might as well read a whole lot of bytes, right. So, you would typically read or write in units called pages, which are it could depend upon the particular computer system, but it could be in this range 2 to 16 kilobytes. Okay. So, you read this much amount. So, this would be one page sitting here, and you read this much amount of data and it will be moved into the main memory. This is reading. When you are writing, similarly, you would write back an entire page. Okay. Now, so what are the problems associated with this? We have to organize our search tree in such a manner that first it can sit suitably on this disk. As I said, our search structure itself is going to be so large that it cannot fit into the main memory, right, and that is what we are going to do over the next slides. So, when you have a disk based algorithm like this, the running time is going to be measured in terms of the time taken by the CPU and the number of disk accesses. Right. Now, this time, the time taken by the CPU is insignificant compared to the number of disk accesses, the time spent in each disk access. So, what you would do in most of these algorithms is to organize your data in such a manner such that the number of times you have to access the disk is very small, right. And what I have said is, so till now we have seen algorithms which are what are called main memory algorithms, where the entire data sits in the main memory. So, they cannot be easily ported to this model when you are, when part of your data has to sit on a disk, it cannot be ported in a straightforward way. So, what are the problems that are going to happen now that we have data sitting on the disk, right? So, one is as far as this pointers business is concerned. Pointers is the same as references to objects, right. So, till now we had a reference to an object, we knew that that corresponded to an address in the main memory. So, you would go and access that location in the main memory. Now, if part of your data structure is sitting on the disk, right. So, just imagine that your red black tree or whatever it was, part of it was in the main memory and part of it was sitting on the disk, right. Now, one of those pointers, one of those references is referring to a location on the disk now, right. So, if it is referring to something in the main memory, then you can go and get it at that particular memory location, but if it is referring to something on the disk, then you will have to do something. Let's use the operation disk read to read a particular data from the disk, and disk write to write back data. So, you will have to use such kind of operations to be able to access that data. Right. I will come to what key means in a short while. Okay. So, one big problem is that the pointers now have to be translated suitably. If your pointer is just pointing to a memory location, then it is easy, you can just get to the memory location and do your job. But if it is not pointing to a memory location, if it is referring to something that sits on the disk, then you have to first fetch that block of data, that page of data from the disk into the main memory, and then you can access that particular object. Yeah. So, a typical pattern would look like something. So, X is a pointer to some object. So, you would read this object from the disk, you will do some operations on this object, and then you will eventually write it back, right. And you might omit this step if you did not modify the object at all, right. So, we are going to work with two operations today, disk read and disk write, reading a block from disk and writing a block back to disk. So, now let us come to what a B tree is. So, B tree is the same as your A B tree, right. So, here I have drawn an example where in this A B tree each node has 1000 keys. So, your value of A here is at least 1000, let us say is 1000. So, recall in an A B tree each node has at least A children and at most B children. So, here I have taken my value of A as 1001. So, each node has at least 1001 children. Okay. So, here I have just tried to illustrate why is this data structure now useful for disk based access, right. So, you have this first node which has 1001 children, right, and since it has 1001 children, how many keys would it have inside it? 1000 keys, right, and I have just organized it very uniformly, so that then each one of these nodes also has 1000 children, and then furthermore these leaves. So, it is just a 2 level tree, these leaves also have 1000 keys in them. Okay. So, how many keys are there in all in this? So, that is 1000 plus a million, yeah, plus a billion, right. So, there will be so many keys in this entire 2 level structure, right. So, let us say I had a database with so many records, right, so many different accounts. So, I could put those. So, for each of the accounts or records, let us say the key is just the account number. So, I could put all of those keys into this kind of a structure, right, where each node now contains 1000 keys. Now, this entire structure cannot fit into main memory, right. You can see this is already 10 to the 9 keys, right. With each of the keys there is associated a pointer. Each of the key itself could be, let us say, 4 bytes of memory. So, 4 bytes of memory, let us say, and 4 bytes of pointers is about 8 bytes per key. So, that is 8 bytes times a billion, right, that is 8 gigabyte. Okay. So, you need that kind of space just to keep this data structure into your main memory. And here we have not said anything about the data associated with these records. Each of those data themselves could be 100 megabytes, because I have my account has listed with it all transactions that have been done on that account, let us say in the last 3 years or 4 years or some such thing, right. So, that is huge amounts of data that, let us say, is stored on the disk. We are not even bringing that into the main memory. But what I am pointing out first is that even if the actual data was stored on the disk, just to be able to access the data just using keys and pointers is so huge that you cannot have all of it into the main memory, right. Now, why is this kind of a structure useful then, right? We are talking of disk based access, right. So, what we are going to have now is that we are going to have this structure, this is called a B tree now. This structure itself would be kept on the disk. So, each of these nodes would now be one page on the disk, okay. And it is just this very top node, the root node, which will be kept in the main memory. Yes. Now, what happens if you have to search? What would you do? You will determine which of these 1000 keys, between which 2 keys your particular key lies in. Suppose it lies, and then go to the appropriate child node. So, suppose this is the child node you have to go to. Now, what will you do? You will access this node from the disk and bring it into memory, right. And from here you will determine key which should be your next node. Suppose it is this node. So, you will access this node from disk and bring it into main memory, and from here you will be able to find your account number, and then you will follow that to get the account data, let us say, right. So, how many disk accesses would you need? One to get this, one to get this, and one to maybe get the actual data associated, the information associated with that particular record that you are trying to access. Yeah. So, how much disk accesses, how many disk accesses do you need? Height of the tree, right. So, to reduce the height of the tree, you want, what do you want? So, you want as little height as possible for the tree, yes. So, you want what, how can you reduce the height of this tree? Increase the value of A, you increase your whatever the number of children each of these nodes have, right. But what is limiting you from increasing the number of children each of these nodes had? Page size, right. Instead of 1000, why didn't I put 10,000 in here or 100,000 keys in here? That would have been even better, right. That would reduce the height even further. If I had, yeah, that would reduce the height even further. But I cannot put too many, because each of those keys is taking a certain amount of space, and I can only put as many keys as can fit into one page. And what is a page? Page is the unit of transfer between the disk and the main memory. So that is defined for a particular computer system. अगर आपका पेज साइज जो है 16 किलोबाइट्स है, so and depending upon if each of your keys comma pointer pair is taking, let's say, 8 bytes, right? Your page size is 16 kilobytes, each of your key comma pointer pair is taking 8 bytes, then you can put at most 2000 keys into one page, right? And so that determines कि आप कितनी branching कर सकते हैं tree में. So this is just reiterating what the node. So x is now referring to a particular node. So what does the node x have? N of x is the number of keys in that node, right? And then once again the first key is going to be less than the second key, is going to be less than the, so key 1 of the node is less than the key 2 of the node, and so on and on. So there are, so n of x keys, and they will have let's say a method or a particular bit in a node which specifies whether the node is a leaf node or not, right, whether it has any further children. So leaf, if this is true, then that means it's a leaf node, otherwise not. And if it's not a leaf node, it's an internal node, then we will have, if there are n of x keys, then we'll have n of x plus 1 children of that node. Yeah. And this we all know, we've seen this before. If k sub I is a key in the subtree C sub I, then k sub I is less than the ith key in the node, right, and so on. So it's the same. So B tree is essentially the same structure as your AB tree, right. Now the only difference is, so for an AB tree we provided a lower bound on the value of B. We said B should be at least, someone remember, 2a minus 1, right. Now today we are going to say that B should be exactly, sorry, so what are we saying today? We want that B should be right. So, so if your node has degree t, so t is the same as the a that we had talked of. All nodes except the root have between t and 2t. So this, so we want that B. So today we want basically, this is our bound for B. So we are working with B equals 2 times a. Exactly. Right. So a B tree is essentially a special kind of a AB tree with B being exactly 2 times a, right. So each node has between t and 2t children, and so it has at least between t minus 1 and 2t minus 1 keys. So the other way in which a B tree differs from a AB tree is that while AB tree is meant to be a data structure meant for internal memory, right, B tree is a data structure meant for secondary storage. So you really have to choose a large value of B so that the height of the tree is as small as possible, and the entire node, the keys, all the keys in the node can fit into one page, right. And the same as before, the root node has between 0 and 2t children. Actually I have said 0, but it need not be 0, it could be 2, between 2 and 2t children. Let us make it 2 and 2t. Right. So this has the root node in this example has exactly 2 children, and then this has t minus 1 keys and let us say t children. So this is the setting in which the height of the tree is as large as possible, right, because each of the nodes has only t children. So this is all just making sure that you remember things from the previous classes, right. So there are 1 node here, 2 nodes here, 2 t nodes here, and so on. So if this goes up to height h, you can compute, this would be the total number of nodes that you would have, and since n is equal to this, that will give you the height of the tree as this quantity. Okay. So searching, so I'll just show you some pseudocode also for searching, so that these things are completely clear in your head. So suppose I am searching for a key k in a node x, right. So, this will be a recursive search procedure. What am I going to do? I am going to first find out the key. Yeah. What should I do? I first have to find out the key, the first key which is larger than k. Yeah, the keys are arranged in, let us say, increasing order in a node. So, I have to find out the first key which is larger than k. So, that is what I do here, right. I keep moving till I find a key which is larger than k. Then I come out. So, I found a key which is larger than k, let us say that will give me the ith key, right. So, if I have found exactly the key I was searching for, then I return. If the node that I am in was a leaf node, that is I cannot proceed any further, then I return nil, saying that the key is not there, else I fetch the next node. I fetch the next node and I continue my search in the next node. Right?
Please repeat this, the last part, else discrete.
What do you have to do here? You were searching, right. This is, let us say, CIX. So, you have to now access this particular node. So, CIX is just the reference to the child node, the appropriate child node. So, you just have to access that. Okay, I am going to skip this. Okay, so splitting nodes, the same idea as before. When do you split nodes? When they are full, right. So, how many keys can sit in a node? We said 2t, 2t minus 1. It can have 2t children, so it can have 2t minus 1 keys. So, if it has 2t minus 1 keys and a new key, we are trying to insert a new key, then we split the node, right. And what was the process of splitting? If this is a node that I am splitting, let us say t key value is 4. So, this already has 7 keys. If I am trying to put one more here, then I need to split it. So, S goes up and this gets split into these, right. So, I have put down the code here. You can have a look at these slides separately to understand this code. I am not going to spend too much time doing it here, right. It is very straightforward what you have to do. This is a procedure for splitting a node y whose parent is x, right, and this is, let us say, the ith child of its parent. So, I refers to that, and what do? You create a new node z, right, and then you have here first you copy the appropriate number of keys t minus 1 keys from y to z, right, that is what is being done here. And then you also, if this is not a leaf node, then you will copy the children also from y to z, that is being done here. And then right, so you are copying that, and here you are moving. So, this has to be promoted up here, right, which means that these keys in here have to be moved one step right in the array. That is what is being done here, and then this key that is to be moved up is copied into the appropriate place there. And then we have these 3 disk write operations, because we have modified this node and the new node we created. So, they all have to be written back to disk, right. So, that is being done there, right. So, it is the same thing as before. The only catch today is that we are doing these disk operations also. You can look at these slides and understand the code. So, how much time does it take for? So, now today we are going to be measuring running time in terms of the number of disk accesses that we have to do. So, in doing a split, the number of disk accesses we had to do was 3, right, because we did 3 input outputs at the end, right. The time, the CPU time, which will now be proportional to the number of keys in the node, right, because we had to move certain keys and so on, is going to be fairly small compared to this, right. So, we will actually be counting time in terms of the number of disk accesses. So, today one variant of binary of B trees also works with. So, if you recall inserting, when we did inserting in 2,4 trees or in AB trees, we went down the tree, found out the place where we had to insert the element, then tried to put the element there, right. And if that resulted in the node getting split, we split that node, and that meant that we had to insert a key in the parent node, and that could lead to another split and so on and on. There is another way of doing this thing, which is that we start from the top, right. So, that is called a two pass operation, wherein first you come down and then you go up the tree. One possibility is to do the entire thing in only one pass. What does that mean? That as you are starting from the top, you check to see if the node that you are looking at already has its full quota of keys. What is the full quota? 2t minus 1. If it already has 2t minus 1 keys, then you are going to split that node right there and then, and only then proceed down the tree. Does everyone follow? So, we are going to start from the root and we are going to recursively travel all the way up to the leaf, but before we descend to a lower level, we make sure that the node contains strictly less than 2t minus 1 keys. If it has 2t minus 1 keys, right, then we split the node right there. Okay, let us understand this. So, I come back to this slide later. Let us look at so, let us say this was my root node, right. I have not yet inserted the key, right. This was the very first root node that I encountered. This is already full. I am working with t equals 4, right. So, this has 2t minus 1 7 keys in it. This is already full. So, before descending down, I see that this is already full. I will write at this step, split this node into A, D, F, L, N, P, and H moves up, right. And now I will continue down the tree, wherever whatever key I am trying to insert, I will now continue. Okay. Right. So, let me see, let us show you an example. I will skip this slide and come back to this later. So, let us take an example and then we will look at the code again, right. So, suppose this is the tree, I am trying to, t is the value of 3, I am trying to insert B. So, first I come here, this node is not full, right, t is 3. So, a node is full when it has 5 keys in it. Yeah. So, this is not yet full. So, I can come down and B is inserted at this place. Now, suppose I am trying to insert Q. So, once again I come to this node, right. This is not yet full. So, I go down. So, actually this should be here. I come here, this is not yet full, I come down here, okay, and then I put Q here, but this is full already. So, which means it will cause it to split. So, Q R S would go on one side, U V on the other, and T gets promoted here, right. Now, note the very interesting thing. Why did this node not get split?
Because because 2t minus 1 अगर full हो तो
Right. So, see, so in the previous in what we had seen in 2,4 trees or in AB trees, what was happening was that when I inserted an element into the parent could also get split. Now, that is not going to happen here anymore. Why? Because I came down from the parent only when the parent had room in it. If the parent had room in it, then when I came down and I split this node and I put one key into the parent is now not going to get split, right. Let us see with this happening again. So, now when I am trying to insert the next key, let us say L. So, and now when I come to the root node, I will straight away split this because this is already full, right. Does not matter where L is going, L is L M N O, M L M N O, it will come here, this node is not full, right. So, but when I am trying to insert L, I will right away split this into G M T X P and then come and insert L here. Okay. Now, let us say when I try to insert F, I come here, this is not full, so I can continue, this is not full, so I can continue, then I come here, insert it here, split it, and one guy gets promoted here. So, the fact that this was not full lets me accommodate an additional key here without causing a ripple effect in the splitting process, right. So, this can be, so in some sense this is like a one pass, in just one way down we have kind of accessed all the nodes. In just a single pass we have accessed all the nodes of the tree and did whatever splitting that needed to be done, right. So, how many disk IOs are required? Basically you just have to move down the tree once, right. So, you have to access every node, and then every time you split a node, right, you have to write down that node back to the disk, its parent node back to the disk, and one new node that you create back to the disk. So, for every time you split, you might have to write down 3 nodes back to the disk, right. So, you will have to read as many nodes as the height of the tree, and how many nodes will you have to write back? You will have to write back at most 3 times the number of split. That many nodes you will have to write back to the disk. Yeah.
So why are we doing this, like with while we decide we keep splitting? Why are we doing this only here, not in the previous case of 2-4 trees? Like,
okay, so towards the end I will discuss what are potential disadvantages of doing it this way, right. If you keep splitting, right, because you will have to now see what I am going to do when I have to delete a key, right. There I will try and let us see what I will try and do there, and then it will be clear, right. So, when I am doing deletion, so I am going to actually skip that code that I showed you, right. You can look at those slides and understand them on your own, right. As far as deleting keys is concerned, once again you recall the earlier procedure. We went down the tree, we deleted a key. When we deleted a key, that node could have less number of keys than it was supposed to have, in which case we first tried to borrow, if not successful, merge. If we merged, we had to remove one key from the parent. That could cause a ripple effect again, a cascading effect, so that we ended up doing this all the way up to the top, right. Now, we are again trying to do a single pass delete procedure, right, which means that we are just going to go down from top and do the deletes, right. So, now what we are going to do is, if we encounter a node which has already the minimum number of keys. What is the minimum number of keys in a node? T minus 1. If it has just T minus 1 keys, then right then we are going to make an effort to let it have more than T minus 1 keys, strictly more, at least T. So, what are we going to try and do? The same thing as before. First we try to borrow from a neighbor, from a sibling. If we are successful with that, great. If not, then that means that the sibling also has T minus 1, and then we merge. And when we merge, we bring one from above. And why can we now successfully bring one from above?
Upper does not have the leaf.
Because the upper has strictly more than T minus 1, right. So, you can do the entire thing in a single pass in exactly this manner. So, that is what is being said here. Before descending to a lower level in the tree, make sure that the node contains at least T keys. Yeah. In the case of insertion, we required it contains strictly less than 2 T minus 1 keys. Now, we are saying that it contains strictly more than T keys, right. So, suppose this is the situation. So, we are once again working with the T equals 3, right. T equals 3 means each node has to have at least 2 keys, right. So, this node, it is okay, there is no problem with this node. Why? Because it has 3 keys. So, I can continue down. I come to this node and F is deleted from here, and there is no problem, right. But if I was trying to delete something from here, then when I encounter this node which has only 2 keys, the minimum number, then I will try to do something right then and there before proceeding down. Okay. Right. So, this is the so I have actually put down all the cases here where the key that we are trying to delete is not in the leaves, then you have to do all of those swaps. So, we have seen all of this before. So, let us just skip some of this, right. And this was the case when we have to merge, right. So, sorry, just one second, let me make sure what. Right. So, this is a setting, if the particular node has only t minus 1 keys, then we have to take action to ensure that it has at least t keys before we continue down. And the first thing is that we can borrow from the sibling, and if not, then we merge, right. So, this is the picture. Yeah, let us look at this one. We are trying to delete B, we come here, there is no problem here, and when I try and delete here, I have to borrow 1 from the sibling, right. You have seen many examples of this by now. So, how do you borrow? 1 goes up and 1 comes down. So, this is the situation happening here. And if you cannot borrow, then you merge, same as before, you are deleting D, you come here, you delete. Okay, so actually sorry, so you come here, CL, when you are deleting D, this already has a problem, right, because it has a minimum number of nodes. So, you are going to try and borrow 1 from the sibling, but you are not going to be successful in borrowing 1 because that also has a minimum. So, you merge and you get CLPTX, right, by bringing 1 down, and then you go ahead and you delete D from here. So, this is the situation that is going to happen. Now, this also illustrates why this is a bad scheme. Who can tell me why? So, this is answering the question that he had raised, right. Why did not we do the same thing for the red black trees and the AB trees?
So, we could have deleted easily, even then we are merging the two.
Okay, but is there, but
increases the number of comparisons, because at every level, in the earlier case we are at the lowest level, we are having the complete node, complete tree. But here at the top it is 0, so we have to make more comparisons.
okay, I am looking for one other answer, which is perhaps, who can, huh?
Because of this, now if you need to insert
Good.
something else, we need to
Split again, right. So, see what is going to happen. So, I just deleted, right, and this is the picture I got. Now, suppose I insert now, what is going to happen? I am going to go back to this one. Suppose I delete, I am going to come back to this. Suppose I insert, so it is kind of going to go, back and forth between this, and I am spending a lot of work in doing this, right, because splitting a node, lots of pointer movements and all of that. So, this scheme does not work very well when you have this kind of a thing happening, right. Your inserts and deletes are, very highly interspersed. If you have a block of inserts and a block of deletes happening, then it is okay, then you can still work with the scheme fine, right. Because if you had just deletes happening, अब इसके बाद भी next delete ही हो रहा था, so there would be no problem, right. This has a large number of keys now, so it can handle a whole lot of deletes without significant trouble, right. So, if you had a large sequence of deletes, then this is a fine strategy, or if you had a long sequence of inserts. But if you had these things alternating very often, then you would be in some trouble. Right. So, once again, what are the disk IOs going to look like? So, we are going to read as many nodes as the height of the tree, and at each point when I am borrowing 1 from the sibling or merging 1 from the sibling, I am basically modifying only my sibling node, right. So, if I am doing any of those operations, I might have to write back my sibling, my own node, and the parent node. Why the parent node? Because even when I am borrowing from the sibling, 1 key goes up and 1 key comes down from the parent, right. So, the parent node also gets modified, or even when I am merging, again the parent node gets modified. So, every time I do some borrow or merge with the sibling, I will have to write back 3 nodes, right, and so that gives the number of disk writes that you have to do at the end of this. So, again this 2-pass operation we have actually seen before, right. So, this was the single pass way of doing things, but 2-pass we had already seen. So, you first go down and then you go up as much as is necessary, so to say. Yeah. Okay. But in the case of disk accesses, you have to think carefully, or you have to organize these things more carefully, right. Because if you are if you first make one pass down and then you make a pass all the way back up, then you are spending twice as much time as you could have by just having made a single pass. Right? So, one thing you can do is that when you are making the first pass down, you keep all those blocks that you read in memory. How many blocks is that? How many pages is that? Just the height of the tree, which is not too much. So, you keep them in memory. Why do you keep them in memory? Because you might require them on the way back on your second pass. Yeah. So, those are optimizations that you can do to try and reduce the time, because as I said, most of the time here is spent in the disk access. You have to reduce the number of disk accesses as much as possible. Okay. So, with that we are going to end this class today. So, this was mainly meant as a recap of the data structure that we saw today was just a small extension of the AB tree, but it is specifically for disk based accesses and is useful in that setting.